In this question, we are going to find the magnetomotive force that produces a total flux of this. So I can say given total flux is equal to 1.2 times 10 to the negative 3 Webers. And I want to find MMF. Varnish on the lamination accounts for 10% of the thickness of the lamination. So what we have here is we have a laminated section. We have a laminated section. And as you know, we make laminated sections to control the eddy currents, to limit the eddy currents that are created inside a magnetic circuit, because eddy currents are losses. Eddy current losses create the heat that happens inside a transformer and also the noise that happens inside a transformer. So this laminated section is sitting in here. This laminated section is sitting in here. And if I were to take this laminated section and draw it, let me take this laminated section and draw it over here, it would look like this. It would have a section of steel and another section of steel, etc. And it would continue like that with sections of steel. And in between those sections of steel, I would have fiberboard in between those sections of steel. And the fiberboard has the permeability of free space. And then there are the strips of sheet steel. So if this is sheet steel, then I know the BH curve. We know the properties of sheet steel. That's on the BH curve for sheet steel. And what the BH curve gives us is, therefore, we know the permeability of sheet steel. We also know that permeability is not just one number. Permeability is, it varies, and it depends on where you are on that BH curve. But at any rate, I can find out that number. And then in between, it is laminate. So it's fiberboard or something. Let's say it's fiberboard. So not magnetic. Laminate. It is not magnetic. And in the question, it doesn't say what these little strips are made out of. We know that they have the permeability of free space. And then we also know the varnish. Oh, it's varnish. It's going to be varnish. It's made out of varnish, not fiberboard. It accounts for 10% of the thickness of this laminated section. So it is 10% of laminated section. So in this what that means is, in this laminated section, it is 90% of this height, So we're looking at geometry here. 90% is steel. I forget what it was. It's sheet steel. And 10% is laminated. Why do we care about the 90% and the 10%? That's geometry. Geometry. So the actual height, or the actual length that a magnetic field would go through, let's say, and this is how laminates work. Let's say I have flux going through this whole thing, which I do not in this problem. then the mean path length, which equals L, would actually be L laminated is actually the total length L times 0.9 of actual steel. So what the laminates do is they just reduce the mean path length. Now that's not applicable in this problem because the flux actually comes down and turns a corner, so it doesn't go all the way through. But let me write down in general how this applies to you. Let's put a star beside it because it's really important. Laminations simply decrease the mean path length. So if you have 10% laminations, then your mean path length is 90% of the length of the square of the, of the geometry. If it's 50% laminations, then the mean path length is 50% of what the geometry looks like because only 50% of it is where your flux flows. All right, that's all this matters here. So let's take a look at this actual problem then. And what does this mean in terms of our actual problem? Well, if I look in my problem, this is 2.5 centimeters. I've got that from the question over here. This is 2.5 centimeters total. 2.5 centimeters total. And that includes sheet steel plus laminates. But the sheet steel is 90% plus laminates is only 10%. Yes? 90% is red and 10% is yellow. So 90% of this height of 2.5 centimeters and 10% of 2.5 centimeters. That's what this means. But the magnetic circuit only cares about the steel part, the magnetic part. But we only care about magnetic part. Okay? So then we can think about this. Therefore, we can think about it as basically a bar magnet. A steel bar magnet. Okay? But it wouldn't be 2.5. And I don't love thinking about it like this. I just think about it as a reduced section, but this might help some people that the thickness is now the thickness of this bar. I've removed the laminates and it would be 90% times 2.5 centimeters. That would be the thickness of this bar. So you can think of it like that. All right, but this question asks us to find MMF for the whole circuit. So this is a little bit of a divergence into what do laminations mean and what do they do for us in this problem. So that's how we're going to handle the laminations in this problem. So let's look back to this problem. It asks us to find MMF. Well, I like to do problems sort of, from what we have to find. So I would say the solution then would be, we would start with whatever MMF is. MMF equals FM, however you want to write it, FM. And we know that that is a relationship between the flux times how reluctant that circuit is to let that flux get established. Flux is given in the problem. Flux is given, and we have to find Rm. Well, Rm is a little bit complicated because it is it's a shape that has two different materials put together. So then we have to recognize that Rm total is what we need here. But Rm total is going to be the sum of the reluctance from the rest of the circuit. And that's going to be the reluctance of this shape plus the reluctance of this laminated section at the bottom. And we can call this cast because it's made out of cast, and we can call this sheet because it's a laminated sheet. So it's going to be the sum of Rm cast plus Rm sheet. This is cast and this is sheet. Just looking back up to the problem here. This is cast. I didn't make that up. It's simply just in the problem. And this is sheet. They both have a different reluctance. So we have to add them together. So this is what we're going to be finding. And we're just going to have to do a series magnetic circuit there. All right. So we're going to have to find this, this Rm. So we're going to have to look at the cast piece and the sheet piece. Let's draw again this cast piece and draw the sheet piece. Here's the diagrams that we have to make. And remember, what we have to do here is we just have to calculate the reluctance for this formula because we want to solve for Fm. And so we need the reluctance of the cast section plus the reluctance of the sheet section. This is what the cast section looks like, and this is what the sheet section looks like. So let's start with Rm of the cast section. Because we don't have any laminations, so that might be a little bit of a simpler spot to start. Simply our equation that we've always used, Rm is equal to mean path length over permeability of the cast section times cross-sectional area. And I'll just put a subset cast here, C or cast. So that's a formula that we are going to have to use to find the Rm of the cast section, where L equals mean path length, which is the average path length that the magnetic lines of force are going to travel. Permeability of the cast is permeability, which we'll talk about later. And A is the cross-sectional area, which we should know what that is here. It is going to be just the cross-section of the bottom here. If I were to look at what this cross-section is, that would be 4.8 centimeters is the length, and the width is 2.5 centimeters. I'm assuming it's the same here and here. So that would be 2.5 times 4.8 centimeters squared. And in order for our equations to work, we really need to convert those square centimeters into millimeters squared. So how many millimeters are in 1 centimeter? We have 10 millimeters in 1 centimeter. we are squaring. And if I worked that out, if I took the time to work it out, I get 1.0 times 10 to the negative 4.
So, Karen,
Yes.
I thought it was 4 centimeters, not 4.8.
Oh, I'm sorry. This is 4.0. Thank you so much. This is 4.0. I didn't read my own writing there. And actually, we don't need it in millimeters. We need it in centimeters. I am forgetting. We need it in, I mean, in meters. We need it in meters. Okay, let's get focused here. 4.0 centimeters, and we want to get rid of the centimeters squared, and our equations actually work in meters squared. So now we have to say to ourselves, how many centimeters are in 1 meter? Of course, there are 100 centimeters in 1 meter. We need to square this because we're doing a squared conversion, and this would be our answer in meters squared. So no problem for A. We'll come back to permeability later. Mean path length is the one that gives us a little bit of a problem in terms of geometry. Mean path length, we'll call that LC for the cast section. And what that means is the word mean really sort of means average. In this case, it means average anyway. And it's going to be the average of the outer path and the inner path. Because some of these flux lines travel on the outside. Some of these flux lines travel on the inside. But we're interested in the flux lines that travel in the middle, kind of like here. In 3D, kind of like here. Yes? All right, there we go. And there's lots of ways to calculate that, but it's going to have to be in the center. So if I were to look at this as a as like head on, then this is a 4 by 2.5, then that mean path length is right in the middle here. Lots and lots and lots of ways to figure out where that mean path is traveling. But if I look at the whole shape like this, then I know it's going from halfway here to here, which is half of this, right? It's this divided into all the way over here, but it doesn't go this whole length. It doesn't go this whole 15. It goes only to here and then back down again. This is my LC. Lots and lots of different ways to figure that out. I'm just going to say the average of, let's highlight some things. It's going to be the average of green path, and let's say purple path. It's going to be the average of those two paths. So I'm going to write down this inner path and this outer path. This outer path, okay? The average of those two. And I'm just looking at geometry. So I'm going to average two things. So I'm going to take half of them because that's just how you take average. And this outer path is 12.5 plus what, 15 over here, plus what, another 12.5 down the side. So it's 15, and then it's 12.5 and 12.5. And those are all going to be in centimeters. And the inner path is going to be, it's going to be 12.5 minus 2.5, which is 10, right? 12.5 minus 2.5, which is 10. The middle is 15 minus 2.5 minus 2.5. So 15 minus 5, which is 10. And this side is also 10. 10 plus 10 plus 10 centimeters. Good. So that is going to be 1/2 of, if we crunch those numbers, 40 centimeters plus 30 centimeters equals, so 1/2 of 40 plus 30 is going to be 35 centimeters. And if I convert 35 centimeters, I no longer want the centimeters, so I put them on the denominator. I want meters. So I do a ratio of 100 centimeters inside 1 meter, which means I need to divide by 100, which means I need to move the decimal places. I'm left with 3 significant digits, 0.35 meters. So the mean path length of the cast section is 0.35 meters. Great. So now I'm just going to highlight this so everybody knows that this was the outer path. And this was the inner path. Okay, so that's the mean path length. So now, what do I know? Let's see here. I know the mean path length because I just calculated it. I know the cross-sectional area because I just calculated it. Let's find permeability. Let's find permeability. We need to calculate this permeability now. So I've grabbed a new color here for permeability. Permeability of this cast section, we can look at that on a BH curve, right? So it is the flux density, B, over H of the cast section. So the field strength of the cast section. And from there, we know that if we can find beta, then we can find H that corresponds with beta on a BH curve. So if we know beta, we can find H using a BH curve. A BH curve. And why do we know what the BH curve is? Because we know the material for cast steel. All right, so then we better find beta. Well, beta is just the density. It's how many lines of flux are there for a cross-sectional area. Well, the question told us that there are 1.2 times 10 to the negative 3 Webers. And we better remember there that that was given. Cross-sectional area, well, we've just been messing around with our geometry. We know what the cross-sectional area is. We better choose the correct cross-sectional area, though. So if we're talking about beta, that means the number of flux lines in a cross-sectional area. If I were to look at what that actually means, that means that looks like this. It looks like our flux density. Our flux density is taking a look at the cross-section. And we see these lines of flux. Let's draw these lines of flux, maybe in blue. Maybe in blue, we're going to draw these lines of flux. Whoops. Oh boy, oh boy, oh boy. So when we look at cross-sectional area, it's basically looking at these lines of flux as they come through this cross-section. What I've drawn here is this little part of the cross-section. I've taken this kind of C-shaped object and I've drawn this cross-section here because this flux is going through like this, going through, and then as it's piercing through this cross-section, that's what I've drawn here. Here's the pictures of these lines of flux piercing through. So all it's saying is these are our lines of flux, and beta just means how many over this cross-sectional area. Well, this cross-sectional area, we have this geometry from above. We have this geometry already, and I believe it was 2.5. I believe it was 2.5 centimeters by 4.0 centimeters was this cross-section. Then I can put that in the equation here. 2.5 centimeters by 4.0 centimeters is my cross-sectional area. So I'm doing pretty well, really, because I've also been given the number of lines of flux, which is measured in Weber. So I can compute this. Great. And 2.5 times 4 is 10.0 centimeters. This time it's squared because I multiplied them together. And I can convert that to meters. Centimeters squared in 1 meter squared. There'll be a 100 squared in 1. And so I have 1.2 times 10 to the negative 3 Weber over 1.0 times 10 to the negative 3. Oops, that's not a Weber. Meter squared. And so my flux is going to be 1.20 Weber per meter squared, and a Weber per meter squared is commonly called a Tesla, which is not a base SI unit, but it is commonly used in magnetism. So we just computed that beta equals 1.2 Tesla. Now we have to find the value of H. So from a BH curve, from a published BH curve for whatever material I have here, what do I have? Cast steel. I have to find beta of 1.20 Tesla, and I get H. So here's what it looks like. And at this moment in time, when this much flux is flowing, which is given in the question, at this moment of time, when 1.20 times 10 to the negative 3 Webers of force are established, which is not always the case, but at this period of time, that is the case. So what I would do is I would say, at this period of time, I know that the flux density is 1.20 Tesla. So I'm going to go over and I'm going to say, at this time, what is the magnetic field strength? So this is given. And find what is is magnetic field strength at beta equals 1.2 Tesla. Look at the curve. So when I go and I look at the curve, I can see, which I don't have in front of me right now, but I have looked at it, and you can pop up anything online or from any textbook, and you can see this corresponds with a value. And there might be apps for this as well, or websites that are going to find this for you. It'll correspond with magnetic field strength equals 1220 amp turns per meter. Now that's hard to do. So it's going to be sort of approximate looking at a curve. But in this particular case, the curve that I found, this is what we have here. So now why did I need to do that? Let me remind myself why I did that. Therefore, I think I was doing that for the permeability of the cast section, which is beta over H of the cast section. I calculated the permeability to be 1.20 Tesla. Sorry, the density, the flux density, not the permeability. The flux density is 1.20 Tesla. And I found on my curve that that corresponds to 1220 amp turns per meter of magnetic field strength is happening right now if that's the amount of flux that got established in cast steel. It would be different in other things. I can just throw that into a calculator, keep two significant digits, and I would get this answer, 9.84 times 10 to the negative 4 henries per meter, minding our units. So now we're done. Now we have all of the values. Now we're done. If we remember what we were trying to do at the beginning, we were trying to find R, reluctance. Now we have all the values for RC. Great. So let's calculate RC. RM, which is reluctance, magnetic reluctance of the C section, is LC, mean path length we calculated before, permeability times, which we just calculated, times the cross-sectional area, which was pretty reasonable to calculate. So from above 0.35 meters, we went to great lengths to calculate that. We went to great lengths to calculate this. We just did that. It's here. And then we went to reasonable lengths to calculate the cross-sectional area that was given from our geometry. I put all this in a calculator, and I be very careful about my units. 3.6 times 10 to the 5 amp turns per Weber. And I'm just going to use two significant digits just to be clear there. I'm just going to use two. And that is what I have for RM. So we feel like we're finished because I'm talking like we're finished. We feel like we're finished because I'm talking like we're finished, but we're not actually finished. all we have now is RC of M. So let's go all the way back here and remember what we were doing in the first place. We were finding the magnetic motive force of this whole shape. And to find the magnetic motive force of the whole shape, we have to find the reluctance of the whole shape and multiply that by permeability or by the magnetic flux lines, which we have. So we need to find the reluctance of the cast section times the reluctance of the sheet section. And so far we have found the reluctance of the cast section, which is 3.6 times 10 to the 5. So we've got this part done. Now we just have to do that of the sheet section. So we just have to do this whole problem over again for the sheet section, but it's a little bit more difficult because it is laminated. So hopefully we're ready for that. Let's do the reluctance of the sheet section now. Okay, reluctance of the sheet section. Okay, and we have to remind ourselves what this looks like because our geometry is sitting way far away from us right now. This sheet section looked like this. And it was laminated in sheets. Let's see, it had a length of 15.0 centimeters. And I believe this was 2.5. I'm going to have to double check. The dimension here. It's 4.0 centimeters back here, and it's 2.5 centimeters tall. So here is our geometry, but if we remember, it's actually also laminated. So it has these laminated sections in it, and that matters. Here's some cast steel and some laminations that are yellow there, and that does matter. All right, so to do the reluctance of the sheet is going to be our same equation for reluctance, which is always our equation for reluctance. It is the length of the sheet section over the permeability of the sheet section times cross-sectional area of the sheet section. So let's find the length. So the length of the sheet section. Well, we are going to take a look at how flux goes through this. It goes through like this, and then it goes across, and then it goes up again. That's how flux goes through. If I am going to look at that sort of head on, not in an isometric view, then the sheet section is down here. Then what it's doing is it's coming down, and the mean path is going to be in the middle here, and it's going to go back up again. Now, this straight section is 15 centimeters minus 2.5 centimeters minus 2.5 centimeters. Yes? Now, this section at the side here is going to be 2.5 centimeters over 2. This is 2.5 centimeters over 2. Oh, and this one is actually over 2, and this is over 2, because this little area is 2.5 over 2, and this little area is 2.5 over 2. So what I'm actually doing as I'm going through there All right, what I'm actually doing there is I am going down, over, and up, 2.5 over 2, 2.5 over 2, 15 minus all of those. However, what you're actually doing is we are not really going through that much magnetic material, are we? So we are actually only going through, these are laminated up the side here. These are laminated. So it's actually 0.9 times that distance, and it is 0.9 times this distance. And what doesn't make sense, but here's how we do it. When you're doing a laminated section, you even have to take just the laminate of going across, even though you could be going across inside entirely sheet steel, we still take 0.9. So our mean path length of this sheet, the length and the width is derated by the laminations. So remember that length and width is derated by the laminations. All right. So it's actually L sheet. And I don't like that because the laminations are only going up. They're not going over, but this is how we do it. So it's going to be 0.9 length times width. 0.9 length times width, which is 0.9 times 2.5. Oh, that's area. Sorry. That's area. For our length, our mean path length, is you know what? I was wrong. Our mean path length, we are not going to derate. We are not going to derate. We're only going to derate the area. Our mean path length, we are not going to derate that as laminations because it actually does travel that distance. Whether it is laminated or not, it actually does travel that distance. So it is just going to be 15 minus 2.5 over 2 minus 2.5 over 2 plus 2.5 over 2 plus 2.5 over 2, which equals 15.0 centimeters as we travel through there. However, the area of the sheet is a different story. The area, the cross-sectional area is going to look like this. It's going to be 4 times 2.5, but it is laminated, and we're going to ignore the directions of those laminations. We're going to ignore the directions of the laminations, and we're just going to say the whole area of the sheet is derated by 0.9 and derated by 0.1. So it is 0.9 times length times width, length times width. And so the area of the sheet is going to be 0.9, 2.5 centimeters by 4.0 centimeters, which will give us a 9.0 centimeters squared cross-sectional area that all of this flux is traveling through. 9.0 times 10 to the negative 4 meters squared. So the effect that the laminations have is to reduce the cross-sectional area. So length and width is derated by the laminations for the cross-sectional area, not mean path length. It's an obscure situation that applies only to laminated sections of magnetic circuits, which is clearly difficult to remember. Okay, so now we have L, it is 15. We have A, it is 9 times 10 to the negative 4 meters squared, but we are still missing permeability. So we are still missing our permeability though. So let's calculate what our permeability is. Our permeability of the sheet section is going to be the flux density of the sheet section divided by the magnetic field strength of the sheet section. And we can calculate the flux density of the sheet section is merely the flux density of the sheet section is merely those number of flux lines, which we know from the problem, over the area of the sheet section. And the area of the sheet section comes into question here. The area of the sheet section is, if I were to draw this, it's got a length and a width, and 2.5 centimeters is the length, 4.0 centimeters is the width, but it's laminated. So we listen to ourselves over here, which says length and width are derated by the laminations. Length and width are derated by the laminations. So area of the cross section is 0.9. 90% of it is sheet metal because 10% of it is actually a laminate. So it's length times width of 0.9 length times width. So 0.9, 2.50 centimeters times 4.00 centimeters. And that is going to be, I'll just say 9.0 centimeters squared, which is equivalent to 9.0 times 10 to the negative 4 meters squared. We want to always work with magnetic circuits in meters. That's when our calculations work out with Webers, etc. So we can plug this in here, 1.2 times 10 to the negative 3 Webers of flux going through here. I'm just going to draw what that looks like. That was given in the question. This is the cross section. These are my lines of flux flowing into or out of the board here. I'm drawing them coming out of the board. And divided by, I just calculated 9.0 times 10 to the negative 4 meters. Don't forget to square it. Or really, a Weber per meter squared is not, or per meter is not a Tesla. A Weber per meter squared is a Tesla. This gives us 1.33 Tesla. Why does this make us happy? Well, because now we can look on a BH curve. We have to find one. Find a curve. On the internet, in textbooks, etc., it looks like this. Actually, for sheet metal, it looks more like this. And now I know the shape of the curve and I know one point on the curve. The point that I know is beta in Teslas. So for this particular instance in time, because permeability changes over time, well, it doesn't really change over time. It changes over the course of this circuit. But for this time when I have 1.2 times 10 to the negative 3 Webers of magnetic field flux, 1.2 times 10 to the negative 3, then I can hit this curve and say, what is H? And you can see that therefore on a curve, H, magnetic field strength, when you have that much flux density. is around 900, depending on which curve you look at, but make sure it's a curve of sheet steel, 900 amp turns per meter. So now I have my density and I have my magnetic field strength. I can calculate my permeability. At this point, I've been working so long on this question, I forget why I need my permeability. But let's continue. And I have 1.33 Tesla on the numerator here, which I like to write like that, over 900 amp turns per meter, which gives me a permeability, which means how accepting this cross section is of making this flux, will give me I do not have that calculated separately. I think is around 1.5, 1.48 times 10 to the negative 3. And if you carefully go back in all of the units that we know, this would be in henries per meter. Now I have this. I forget why I wanted that. Let me look up here. Okay, I wanted that because of RM. I wanted RM of the sheet. So and RM I've been doing in green. I remember now. I need RM of the sheet and RM of the cast, and then I'm going to add the two together to get the total series RM and stick that into an FM question because it was asking for FM. So RM of the sheet is going to be L of the sheet over permeability of the sheet times A of the sheet. As I'm writing this, it makes me feel happy because I know I just went to all the effort to compute all of those things. Here we go. 1.48 times 10 to the negative 3 Henry per meter. Cross-sectional area was 9.0 times 10 to the negative 4 meters squared, I believe, which came from over here. And if I were to put all of that in a calculator, I do have the answer to that one, 1.1 times times 10 to the 5. Reluctance is in amps per meter, per Weber. And I'm going to put the unofficial unit of turns in there as well, because it really does make things simpler. The question asked, the original question asked, find FM. Well, and we said that FM equals magnetic flux, which was given, times the sum of the reluctances. And that is magnetic flux times the reluctance of the cast section plus the reluctance of the laminated sheet section. I'm writing big because we're near the end. I was given that the magnetic flux at this point is 1.2 times 10 to the negative 3 Weber of flux lines. And I calculated 3.6 times 10 to the 5, I believe. Plus, we just calculated 1.1 times 10 to the 5. And these are in amp turns per Weber. Okay, so I'm just subbing in because this is a series magnetic circuit. Remembering that it looks like this and this, these are two different materials. This is cast and this is sheet. Therefore, this has a reluctance and this has a reluctance, and we have to add them together. And that's what we just did there, cast and sheet. 5.6 times 10 squared amp turns, or just amps as the official unit. Therefore, the MMF of the entire series circuit is 5.6 times 10 squared amp turns. Quite a long problem, lots of steps, nothing harder than regular magnetic circuits, just a lot more steps involved. Took a couple of pages, but we did it. That's how you do a series magnetic circuit with laminations.